The art of measuring algorithm efficiency. Understanding time and space complexity in the world of algorithms, performance is king. As developers and problem solvers, we constantly seek ways to optimize our code so that it runs faster and consumes less memory. This pursuit leads us straight to the heart of computational efficiency, algorithm complexity analysis. Understanding how an algorithm's runtime grows as input size increases is crucial for making informed decisions in software development. Whether you're designing a search engine, optimizing database queries, or building machine learning models, knowing your algorithm's behavior under different scenarios can make or break your project. Decoding Big O notation. The language of algorithms. Big O notation serves as the universal language for expressing algorithmic efficiency. It abstracts away constants and lower-order terms, focusing solely on how the runtime or space requirements grow relative to the input size. By using Big O, we can compare different approaches without getting bogged down by hardware specifics. This notation helps categorize algorithms based on their scalability. For example, an algorithm with O(n) time complexity will generally outperform one with O(n) superscript 2 when dealing with large datasets. However, it's essential to remember that Big O provides asymptotic bounds rather than exact measurements. Let's consider some common complexity classes. O(1) constant time operations such as accessing an array element by index O, log(n) efficient divide-and-conquer strategies like binary search O(n) linear time processes such as iterating through a list once O(n) log(n) common in sorting algorithms like merge sort and quicksort O(n) superscript 2 nested loops often found in naive implementations O(2 to the power of n) exponential growth typical in recursive solutions without memoization. While these categories give us general expectations, they don't tell the whole story. Real-world performance depends heavily on constant factors and implementation details. A well-crafted O(n) superscript 2 solution might still beat a poorly implemented O(n) log(n) approach for small inputs due to lower overhead. It's also worth noting that Big O primarily focuses on worst-case scenarios. In practice, average-case analysis can be equally important depending on the application context. Understanding both perspectives allows for better decision-making during algorithm selection. Time complexity analysis. Beyond simple counting, measuring time complexity involves analyzing the number of basic operations executed as a function of input size. While simple counting works for straightforward cases, real-world algorithms require deeper examination. We must account for branching paths, recursion depth, and data structure characteristics. Consider a scenario where two algorithms solve the same problem but use different data structures. One may have superior theoretical complexity while suffering from poor cache utilization. This highlights why empirical testing complements analytical methods. It reveals practical bottlenecks that pure theory sometimes overlooks. Recursion introduces additional complexity considerations. Recursive functions often involve hidden overhead related to stack management and function call setup. When analyzing recursive algorithms, we need to carefully examine base cases and recurrence relations to derive accurate time complexities. Data structure choices significantly impact time complexity. An operation that takes O(1) time in a hash table could become O(n) in an unsorted list. Choosing appropriate data structures aligns closely with achieving optimal algorithm performance. Moreover, external factors like I/O operations and system calls shouldn't be ignored. These elements contribute to actual execution times even though they aren't typically reflected in traditional complexity analyses. Balancing theoretical understanding with real-world constraints ensures effective optimization strategies. Evaluating space complexity. Memory matters if time complexity determines speed, then space complexity governs memory usage. Analyzing space requirements is critical, especially in environments with limited resources or strict latency constraints. Both aspects together define an algorithm's overall efficiency profile. Space complexity considers auxiliary storage needs separate from input data itself. This distinction matters because many algorithms require temporary storage proportional to the input size. Understanding this difference enables precise resource allocation planning. Different types of variables affect space consumption differently. Primitive types usually take up minimal space compared to objects which carry substantial overhead. Arrays and other collections further complicate things by requiring contiguous memory blocks that vary in size depending on contents. We must differentiate between in-place versus non-in-place algorithms. In-place modifications preserve original data at the expense of potential instability, whereas non-in-place versions create new copies. Each choice has trade-offs affecting both time and space requirements. Caching in memory hierarchy effects add another layer of complexity. Modern computers employ multi-level caches that drastically influence perceived performance. Algorithms optimized purely for theoretical metrics might perform worse in practice due to poor spatial locality. Amortized analysis. Seeing through average performance, some algorithms exhibit varying performances across individual operations. Amortized analysis offers insight into average case performance over sequences of operations instead of focusing only on single instances. This approach proves particularly useful for dynamic data structures undergoing frequent changes. Take, for instance, the classic example of a dynamically resizing array. Individual insertions can range from O(1) to O(n), depending on whether expansion occurs. Amortized analysis shows that over time, most operations remain efficient despite occasional costly expansions. Other examples include hash tables with load factor adjustments and union-find structures with path compression. These cases demonstrate how amortized cost calculations provide more realistic performance estimates than worst case alone. Using amortized analysis requires careful consideration of operation frequencies and costs. It's an advanced technique best applied after establishing baseline complexities through standard methods. Combining multiple analytical tools gives a complete picture of algorithmic behavior. Empirical benchmarking. Bridging theory and practice. No matter how sophisticated our analytical techniques are, nothing replaces hands-on benchmarking. Empirical evaluation measures actual running times against various input sizes and configurations. This method exposes performance nuances that mathematical analysis alone cannot capture. Benchmarking helps validate theoretical predictions and identify unexpected bottlenecks. It's invaluable for comparing competing algorithms within similar complexity classes. Small differences in constants or hidden factors often determine practical superiority. Effective benchmarking follows systematic procedures. We test multiple implementations, vary input parameters systematically, and ensure fair comparison conditions. Statistical analysis of results enhances confidence in conclusions drawn from experiments. However, benchmarks must be interpreted cautiously. Results depend on numerous environmental variables, including CPU architecture, operating systems, and compiler optimizations. Reproducibility remains a key challenge in experimental validation efforts. Combining theoretical analysis with empirical verification creates a robust framework for evaluating algorithm performance. This dual approach ensures we select the most suitable solutions for given problem domains. Choosing between competing complexities, selecting the right algorithm hinges on balancing complexity trade-offs. Sometimes choosing between slightly higher time complexity versus significantly reduced space requirements becomes necessary. Context-specific priorities dictate these decisions. For embedded systems with severe memory limitations, favoring algorithms with lower space complexity might outweigh concerns about marginal improvements in time efficiency. Conversely, high-performance computing applications prioritize raw speed above all else. Real-time systems present unique challenges where predictable response times are paramount. Here, deterministic algorithms with known upper bounds become preferable regardless of average case performance gains offered by alternatives. When working with big data processing frameworks, distributed computation capabilities change the landscape entirely. MapReduce paradigms allow handling massive datasets efficiently even if individual components would struggle with them independently. Ultimately, there's no universally correct answer. Successful practitioners develop intuition through experience and apply analytical skills judiciously according to specific project demands. Advanced techniques in complexity analysis. As problems become increasingly complex, standard analysis methods reach their limits. Advanced techniques help navigate intricate scenarios involving concurrency, probabilistic behaviors, and quantum computations. Probabilistic analysis introduces randomness into algorithm design, offering expected performance guarantees rather than absolute assurances. Randomized algorithms find applications in cryptography, networking protocols, and approximation schemes where precision isn't always feasible. Concurrent algorithms introduce synchronization overheads that impact both time and space efficiencies. Managing shared state safely adds significant complexity beyond sequential counterparts. Correctness proofs become substantially more challenging in parallel contexts. Quantum computing presents revolutionary possibilities yet introduces novel forms of complexity measurement. Quantum algorithms leverage superposition and entanglement properties, leading to fundamentally different efficiency profiles compared to classical counterparts. Multidimensional complexity analysis extends traditional metrics to handle simultaneous variations along multiple axes. This approach proves essential for optimizing distributed systems where interdependent components interact simultaneously. These advanced topics illustrate how ongoing research continues expanding our understanding of algorithmic efficiency. Staying current with evolving methodologies ensures we maintain competitive edge in rapidly changing technological landscapes. Common pitfalls in complexity assessment. Even experienced programmers occasionally fall prey to misconceptions regarding algorithm complexity. Recognizing these pitfalls prevents flawed designs that appear efficient but fail under scrutiny. A common mistake involves confusing time complexity with actual execution speeds. Just because an algorithm has better asymptotic complexity doesn't guarantee it'll perform better in every situation. Constants and implementation quality play vital roles in determining real-world performance. Overlooking hidden dependencies between variables can lead to incorrect classifications. Some seemingly linear time algorithms contain nested iterations masked by clever indexing schemes, resulting in quadratic time complexities. Failure to account for memory hierarchies causes mismatches between theoretical predictions and observed behavior. Cache-friendly access patterns significantly influence performance despite identical Big O classifications. Ignoring secondary factors such as disk I/O or network delays skews evaluations toward unrealistic assumptions. Comprehensive assessments require considering full system interactions rather than isolated algorithmic components. Lastly, premature optimization based on incomplete analysis risks creating overly complicated solutions that offer little tangible benefit. Focusing first on correctness before worrying about micro-optimizations yields better long-term outcomes. Conclusion: mastering algorithm complexity analysis empowers developers to build more efficient, scalable solutions. By understanding time and space requirements, we gain the ability to choose optimal algorithms tailored specifically to each problem domain. To continue improving your skills, actively engage with diverse coding challenges that force you to think critically about trade-offs involved in different approaches. Regular practice reinforces conceptual knowledge while developing intuitive judgment about what constitutes good algorithm design.